Good morning to all. I'm your host, Dalvinder Kaur from lovely Professional University. Get ready to dive into today's topic, that is the invisible force, unraveling the mystery of dark energy. Before we proceed further, allow me to introduce the experts of the day. Dr. Shankar D. Pathak, Associate Professor at the School of Chemical Engineering and Physical Sciences, Lovely Professional University. With over 15 years of expertise in theoretical physics and cosmology, Dr. Pathak has over 20 peer-reviewed publications in leading journals and collaborates with scientists worldwide and experts in Mathematica and Python. He combines advanced research with innovative teaching and more. Before we proceed further in today's session, I would like to request everyone for any questions you can write in the chat box or in the Q&A box, and same will be addressed from my side in the end of this webinar. Now I'm going to hand over this session to our expert, Dr. Shankar D. Pathak, and it would be an absolute delight to listen from him. Over to you, Dr. S.D. Pathak.
Okay, so thank you so much for the nice words. So the title of the talk is The Invisible Force. So as it is clear by the title, so force is invisible. So it is not invisible. It is of course the lack of the fundamental understanding of the dark energy. So that's why uh, we are saying invisible or dark term. So let me start the introductions. So what is the dark energy? So dark energy first time introduced by 1998 after the supernova explosions. So when Einstein just give the general relativity equations in which he assumed universe is static. So to maintain the staticness after the discovery of universe expansion by the Hubble, they put the cosmological constant. So that the technical story I will cover is later. So first of all, the few facts about our universe. So first things, the age of the universe is around the 13.8 billion years and about 93 billion light years in diameter. So it's a very huge length. So 93 billion light years. It's a really very huge and containing almost or it will be more than 100 to 200 billion galaxy, and in the typical galaxy you can understand how much the stars and how much the solar system will be there, and each galaxy with the millions to trillions of the stars and countless planets. So you can imagine how big our universe. So yes, this is just the part we can see space continuous, and this is all about the observable part of the universe, and some part that not observable, that will be completely causally disconnected. So in nutshell, our universe is big, big, and very big, right? So today we will explore what is the dark energy and what its theory and what is its connection with the quantum gravity. So yeah, so this picture thanks to the NASA WMAP team. So as you can see here, the beginning point is light part. This is the something Big Bang. So all of you heard about the Big Bang. Space and time, they are condensed at the fixed point, and that point exploded. And after Big Bang, there is a event is called the inflation. Big Bang is exactly happens or not, this is the question mark. And after the inflation, the everything is just started within the fraction of time, the very big size. So you can see here. So after light pattern, this years here the cosmic microwave background radiations, and total is 13.77 billion years, around the 13.8 from the Big Bang to up to this stage. So here as you can see this arc, this is the today's situations, right? So dark energy dominated very near past, and earlier it is the cosmological constant or scalar field. There is the debatable questions. So very good picture. Once again, the thank you to the NASA team. And uh, this one, this arrow, red color arrow, so the flow of the time. time is just going in the forward direction. It is related to the entropy. And today we are here, and galaxy formation and everything is structure formation, as we can see. And it's because of the dark matter concentration and the effect of the dark energy and also the structure formations. So evolution of the universe, again this picture taken from the NASA website, and the links given here. So what exactly the dark energy? Dark energy basically have the power to accelerate the universe. So universe is not only expanding, while it is accelerated expansion. So it is because of the dark energy. And this acceleration is because of uh, this term dark energy, and it's approximately 68% of the universe. Earlier it was 70%, but after the Planck observations, its contains around the 68%. So its nature, repulsive gravity, and very uh, interesting energy, and which completely unknown, the fundamental physics not known yet, and so many things now pending to know about the dark energy, how it is interact with the background matter, and what it's a particle characteristic, everything. So many questions remaining to know. So total cosmic budget, in the picture we will see it. Dark energy contributes to 68%. So most of the part of the universe, that is the dark energy, and not completely no, and they have the potential to accelerate the universe. And second important ingredient, that is the dark matter, which is 27%. And this dark matter can only interact with the gravity, not with the electromagnetic radiation. So since this dark matter not interact with the electromagnetic radiation, so it cannot be detected directly. So only the gravitational effect we have, that can detect it. Again, it is just like the dark energy. It is again very interesting and a potential candidate responsible for the structure formations. And the things which visible are the things which are directly interact with us, that only the 5%. And this 5% covers all the stars, planet, galaxy, and other visible part of the universe. That is only the 5%. So around you can see this 95% of the universe, around the 95% of the universe is completely dark, and that is the dark sector. Dark means it is not like the dark color, it is because of the lack of the knowledge, lack of the fundamental understanding, and no fundamental theory behind this dark sector. So this dark sector mainly consists the two term, dark energy and the dark matter. So dark energy, dark matter combined together known as the dark sector. So 1998, two independent teams, they tried to observe the supernova type 1A observations. I will cover later. So they claim the universe is in the accelerated phase of the expansion. Now the theoretician is struggling to develop the theory why our universe is accelerating, and then they propose it is the dark energy. That dark energy is responsible for the expansion of the accelerated expansion of the universe. So as you can see, in this picture right panel, ordinary matter contribution is the 5%. In the pie chart it is clearly represented. Dark energy around 26%, and this is 69%. It is 2019 data by the Planck, and the dark matter here the 26%. European Space Agency in the Planck mission, they claim this type of the cosmic budget. So this one thing is very clear. So most of the part of the universe is unknown, physics not known up to the marks, right? So again, thank you to the Isha and the Planck collaboration for this beautiful picture. And some fact about the dark energy, these facts established by the observation. So dark energy is the form of the energy that present everywhere in the universe. That is the especially homogeneous, might be especially homogeneous, not especially homogeneous, depending on the assumptions on which you are working. And this dark energy is responsible for the accelerated expansion of the universe. So it is either scalar field or cosmological constant. So in 1988, Bharat Ratra and James Peebles, they uh, published the paper in the Physical Review D, in which they consider the homogeneous scalar field. They have the negative pressure, and they can good candidate, promising candidate of the dark energy apart from the cosmological constant. So two component, two important member of the dark energy, they have the negative pressure, and due to this negative pressure, they have the anti-gravitational characteristics. So how dark energy will appears in mathematical form? So Einstein field equation, this is the governing equation of the gravity, and in which right hand side that is the stress energy tensor. So stress energy tensor, dark energy at the modified matter can see. And simplest candidate, one of the simplest candidate, as I already mentioned here, the cosmological constant, and sometimes it's called the lambda. It is the historically represented by the Albert Einstein cosmological constant, which equation of state means technical term W is equal to pressure over the energy density. This is called the equation of state, which comes out -1, and that's why they have the repulsive gravity. And in ordinary gravity or Newtonian gravity, in 10 plus 2 level, you already know the gravity can attract the things, but the dark energy, they have the repulsive gravity. And yes, it is little bit confusing and not easy to digest how the repulsive gravity, but it is true. When you look the Einstein field equation and solve this Einstein field equation and in the Friedman model, so energy density is not only contribute in the gravitational attractive force, but also the pressure contribute effectively. And if pressure will be negative and dominate over the energy density, and then leads to the repulsive gravity. So that's correct. And apart from the dark energy, there are the few other promising theoretical model. Sometimes it's called the artifact. This artifact is a modified gravity, and rather than the separate force, right? So alternative theory of the gravity, that is called the modified gravity here. They are also responsible for the accelerated expansion of the universe. And as you know, the dark energy having the repulsive gravity, so what its future? See, in future it is predicted and the Occam result approach, big freeze or big rip or another fate of the universe. The things right now it's dominate over the very large scale, and then it will be dominate on the galactic scale, then our solar system scale, and finally it will be dominate on over our planet, then atomic scale, DNA, molecules, everything. So again, we will be reaching the big rip and the big freeze. So this is the consequences and the some fact. Let me move on the some mathematical background. So theoretically, when you are going to deal the dark energy, how this dark energy uh, affect our dynamical universe or dynamics of the universe, then we will go through the some rigorous mathematical calculations. So as a modified matter, why I'm saying the modified matter, in the Einstein field equation, this equation Rik minus half Gik, this is the Einstein field equation. So left hand part of this field equation is called the geometrical part, and right hand part is called the matter part. So this equation can be derived from the Einstein Hilbert action. This action I not mention here, that will be little bit more complicated mathematics. So as a modified matter, so we can tune this Tik, but one can tune the left hand side, the geometrical part, that is the modified gravity. So dark energy, that will be tuned by this Tik, right hand side of the field equation, that is the energy momentum tensor. So that's why its name is the modified matter, and responsible for the accelerated expansion of the universe. And they have the negative pressure, and that's why its equation of state is equal to negative, and it should be minus less than minus 1 by 3. So less than minus 1 by 3, that is leads to the repulsive gravity, and accelerated expansion will be possible. So metric is sometimes not sometimes, it's always known as the distance function in the topology, and it is written like this. Here the k is the curvature parameter. So the two fundamental principle, based on these two principles, our cosmology, our modern cosmology developed, and these two principles known as the cosmological principle. So universe is homogeneous and isotropic. It's very important and it's crucial to know up to what large up to what scale, length scale, it is homogeneous and isotropic, so which is equal to 50 megaparsecs. So 50 megaparsec our length scale up to universe is looks like the isotropic and homogeneous, but the recent observations suggest there are inhomogeneities. So if this inhomogeneity confirm at the large scale, then we need to change our fundamental equations, and again the things will be very complicated in the rigorous mathematical calculations. So anyway, let me come back to the Einstein field equation. As I told you, Tik is the modified matter, which it is the dark energy, and which can be written as rho is the energy density and p is the pressure. U and uk is the four velocity. This is the beautiful equation in general relativity. So this is all about the energy momentum tension. And solving this energy this Einstein field equation, the metric given here, distance function ds square. So you will reach at the two fundamental equation, the governing equation, that is called the Friedman equations. And for simplicity, not and the simplicity as well as observation suggests also our universe is especially flat. And first equation, this is Hubble equations, h square a is scale factor at pi z over 3. Rho is energy density, and it's a time derivative, and its time derivative lead to the acceleration equation. So a double dot upon a, that is read as the acceleration. As you can see, right hand side, 4 pi z by 3 is the fundamental constant, which value will be always positive. And rho plus 3p, so to make it is accelerated part, so the things inside this bracket should be less than 0, it should be negative. So it, if it will be negative, so negative term is here, so overall quantity in the right hand side becomes positive. So this is true for this inequality, and you can see rho plus 3p less than 0 leads to the wp over rho, as I told you all, earlier, equation of state, which should be less than minus 1 by 3. And if it is less than minus 1 by 3, in your hand, accelerated expansion of the universe. So the problem is which type of the energy, which equation of state is less than minus 1 by 3. So Einstein, when he was developing the successful model, theoretical model of the cosmology, and he was assumed the universe is static. So and of course he obtained the insensible solutions. And why they are insensible solutions? Because not in the problem in the assumptions, the problem in the calculations. To make the sensible solution, he put the uh, cosmological constant to make the static of the universe. But recently, of the development of the cosmological model by the Einstein, uh, Hubble confirmed the universe is not static, it is the dynamic. So he withdraw, and you know the famous story. Einstein just claimed biggest blunder of their own life. So again, 1998, universe is accelerated expansion. So the scientists, especially Rees and Perlmutter, they are just think about why universe is accelerated phase of the expansion. So it is because of the some energy which have the negative pressure that dominate over the energy density. And since equation of state is equal to minus 1, so first candidate comes in their mind, that is called the cosmological constant, right? So if W is the constant here, and W is equal to 0 for taking as the dust matter on approximation known as the dust matter. Dust means not it is the dust, it is because of the mathematical approximations. And the radiation in the statistical mechanics, you know it's very well, the ratio of the pressure over the energy density of radiation, which comes out the 1 by 3, and this is a positive quantity. So neither matter nor radiation can accelerate the universe. Only the dark energy have the potential to accelerate the universe via these equations. So going further, uh, the first of the all the questions you comes in your mind, why we need the dark energy, right? So this is all about the blah blah blah, like the dark energy. This is the expansion of the universe. But what is the need of the dark energy? Why we require? So the first thing, first observations, 1998 suggests the universe is the accelerated expansion. And age, if you going to calculate the age of the universe, so age of the universe, when you mathematically calculate, so it is less than as expected, right? So when you put the dark energy, then age will be increased further and further. So this is one strong observation. Supernova type 1a probe 1998, which I already mentioned, and one another probe in 1965 discovered the Penzias and Wilkinson. That is called the cosmic microwave background radiation. In the further slide, I will cover these three important uh, observation, independent observation. They demand there should be change in the field equation. There should be some reason why universe is in accelerated expansion of the universe, right? So other model, as you I mentioned here, FR model, that is called the FR gravity model. that tune the left hand side. As you can go back to the equations, field equation I already mentioned here, Rik minus half GIKR. When you tune this curvature parameter in the Einstein Hilbert action, then you have the also accelerated expansion of the universe. That's proposed by the Starobinsky. And okay, so the candidate of the dark energy. So dark energy, just like the umbrella term, there are the several candidate will be possible. So the two candidate, cosmological constant, sometimes is known as the vacuum energy in the particle physics. It is the simplest candidate, which equation of state is equal to -1. And apart from this cosmological constant, because this having the tension, that the cosmological tension, cosmological constant tension, and about its value, and other two candidate scalar field as a source of the dark energy. So in the scalar field, the several scalar field proposed by the scientists in their different requirements. So quintessence or standard canonical scalar field is the common, and similarly the tachyonic scalar field, which is the non-canonical. Phantom scalar field, it is looks like the quintessence but which have the negative kinetic energy, like that. And some other scalar field is also possible. Okay, so when you are going to deal the dark energy or know the accelerated expansion of the universe, then a few technical terms you need. First is called the co-moving distance, and how it is calculated. It is calculated by this integration. Here the AT is the scale factor. Scale factor means something which are scaling, just going big and big. Suppose you have the initial size of anything which is equal to 2, and after some times it's just become the double. 2 into 2, 4 times, and again it will be become 2, just increase the 2 times. 4 into 2, 8 times. So it just increase 2 times in each time interval. So it is similar to the scale factor, how the scale up, right? So if you know the scale factor, and of course the expansion will be depend in the different way on the scale factor. It is decided by the which type of the matter, which type of the things you are taken, and of course that will be depend on the equation of state. So this is the co-moving distance or coordinate distance. And similarly, with the help of the co-moving distance, another distance is called the luminosity distance, which is very crucial in the supernova type 1A. And this luminosity distance calculated theoretically, and this luminosity distance calculated by observation by measuring the magnitude scale of the supernova. And they can estimate, as you can see, this luminosity distance depends on the Ez is here uh, expansion factor, sometimes called the normalized Hubble parameter, which is equal to Hubble parameter over the Hubble constant. And in Lz, the energy density of the different part of different components of the universe are just incorporated. So expansion factor directly affect this luminosity distance. So one can measure this luminosity distance theoretically and observationally. Then you can estimate how much the acceleration, how much this luminosity distance affected by the expansion. And the same things, luminosity distance, another is called the angular diameter distance. So angular diameter distance, it is very simple physics, length over the radius over the theta angle. So arc length over the theta. And simple straightforward calculations, calculation I will not mention here. If you want to go through all the calculations, I recommend the book Dark Energy, Theoretical and Observation Perspective by the Luca Amendola, where these all are the derivation mentioned clearly. So as you can see, angular diameter distance also depends on the expansion factor Ez, which sit in the denominator inside the these integrations. And Z is a redshift, and this is curvature term, and curvature is a geometrical part. And there is a few relations, luminosity distance and angular diameter distance. So from here, angular diameter distance can be obtained. So supernova type 1A observations. And the question why I'm discussing this all the mathematical stuff here, because when you are enter the supernova type 1A observations, then you need to calculate these all the distances, and then you will be obtain the how much the acceleration will be there. So forget about this all the data. Just come back to this mathematical equation here. So yeah, as you can see, this is magnitude, apparent magnitude is here, and absolute magnitude is here. So directly, observationally, one can measure the apparent magnitude and absolute magnitude. This is the magnitude distance relation, and it depends on the DL. Here is the DL is the distance, and sometimes it's called the luminosity distance. And luminosity is directly related to the magnitude scale. And from flat geometry, this distance, luminosity distance, depends on expansion history via these Hubble parameters. So theoretically, one can calculate the luminosity distance by the HZ. Observationally, one can calculate luminosity distance DL, and they try to match this DL consistent with the theoretical value. But if you are not considering the dark energy, these two values will not consistent. They are discrepancy. But when you add the dark energy, as it is mentioned here, which is equal to 0.7, it is the not a Planck data, it is the WMAP data, Wilkinson Microwave Astronomy Probe by the NASA. So it comes out 0.7 dark energy, it is equal to 0.7. It is a little bit mistake, not should be here. DE is not 0.38. Here the mistake, it should be matter. So matter part is at 0.38 and the dark energy is 0.7. So this demands this provide the direct confirmation. We need the dark energy. Dark energy should be exist. And what is the supernova? Supernova is one kind of the violent explosion of the white dwarf. And white dwarf star is the formation gravitation after the gravitation collapse. So what happens if the star just finished each and every type of the energy, each and every type of the radiation inside? So if the size of the star, mass of the star is not more than sun of our solar mass, 1.4 mass of the star, that is called the Chandrasekhar limit. So the core will be populated by the electron gas, and classically electron gas will be collapsed. But since electrons are considered the fermionic particle, and quantum degeneracy pressure rise, and they will stop the further gravitation collapse, and the things will be stable structure, that is called the white dwarf. But if the mass will be little bit or much more than the solar mass of the sun, then core will be populated by the neutron, and there will be the mechanism, proton eat the electron and the remaining the neutron will be there, and the neutrino also produce. So core will be populated by the neutron gas, which again considered as fermionic particle, and the neutron degeneracy pressure further stop the gravitational collapse, and the system will be stable structure known as the neutron star. So supernova is the intermediate stage and phase where the violent explosion will be occurs of a white dwarf star, right? So there are the different types of supernova, and based on the absorption line, it will be classified into the multiple category: type 2, type 1a, and type 1a. So the singly ionized silicon. So there will be the different classifications. So you know how the supernova type 1a suggests the need of the dark energy. And apart from the supernova, another milestone discovery by the Penzias and Wilkinson, that is called the cosmic microwave background radiation. So cosmic microwave background radiation, in which calculations there will be the shift parameter. So shift parameter, as you can mention here, and as you can see, the shift parameter again depend on expansion history of the universe, right? So just like the supernova, expansion history of the universe affect the luminosity distance, and the luminosity distance can be calculated by the theoretically and from the observations. So similarly, shift parameter can be calculated by the CMBR observations, and then this will be suggest location of the acoustic peak. I will come on the its power spectrum demands. There should be the dark energy, which energy density can be lies 0.72 to the 0.77. So apart from supernova, and it is consistent with the supernova type 1a. So cosmic microwave background radiation is one crucial observation that is also confirmed dark energy should be exist, and how much the dark energy we need for the accelerated expansion of the universe, that will be confirmed by these observations. So what exactly is CMB? CMB is basically our universe is the very hot, and dense in the beginning, right? So in the beginning, cross section was very less, and so Thompson scattering will be there, and the photon not getting sufficient space to pass from one position to the another position. Multiple scattering will be there, and that is just like the fog structure. And it is better to say soup, radiation matter soup. So once the matter will be formed and things is just little bit opaque, and photon is traveling in the universe, and the universe is already expanding, so its energy will be continuously decrease and decrease and decrease. So 1965, Penzias and Wilkinson, they detect this photon, and radiation of that photon and lead to the 2.7 Kelvin, the temperature of the background, and it comes out the background from. So that's where the background from in the radiation, and since it is a remnant part of the cosmic stage, Big Bang stage, the name is the CMB photon. So this photon is starting to travel from the recombination at last scattering surface LSS. So they have the huge information. So all the information about the evolution of the universe. So one can detect this photon. So they can filter. They can know the history of the evolution of the universe. So that's why CMB are very important. And nowadays it is the independent topic of the research in cosmology. So you can see this is little bit mathematical, and CMB power spectrum. So exact power spectrum is looks like the black body radiation power spectrum. So acoustic peak, you can see look the peaks here, and here the multipoles. So acoustic peak amplitude depends on the baryon fraction. Baryon means matter density, and they are made by the baryons and there are leptons. And Hubble constant, so precise data possible revealing the dark matter in the neutrino species. So it is confirmed by the Wine Who and the White, the very powerful paper, 1998 Astrophysics Journal. So for the detail you can go through. And CMB damping tail, you can see here the damping tail at the arc minute scale. So fluctuations, there are so many fluctuations due to the photon diffusion and the finite glass scattering surface of the thickness. And this is all about location of the peak and where the peak, the height of the peaks. They are just give the information about different kind of the contents, as you can see here, 1 minus omega naught, omega lambda, and omega b is the baryon density parameters, like that. So thank you to the Wine Who and White milestone paper through research. And yeah, so after these two, the three observation which I mentioned here, age of the universe, the detailed calculation of the age of the universe are not mentioned here. It can be directly calculated. Supernova type 1a, cosmic microwave background radiations. So these two observations, and not these two only. Another observation, baryon acoustic oscillation, they also confirm the universe is in the expanding stage, and they demand the dark energy also. So cosmology in the nutshell. So old cosmology means initial stage. The de Sitter, Friedman, they develop the cosmological model theoretically, and in the new cosmology, because the Friedman model, they have the serious issue, horizon issue, and the entropy issue, and the flatness issue. So these issues can be resolved by the putting one stage that is called the inflation stage. So inflationary theory proposed by first time Starobinsky and Alan Guth, and Alan Guth is also proposed independently, and Starobinsky also first time just give the inflation theory, and Eric Linder, and scalar field, hot big band structure formation. These all are the things in the cosmology they consider the new cosmology. And now nowadays the people are struggling to develop the quantum cosmology, and what is the successful theory of the quantum cosmology, that is a part of the research. So in the Friedman model, which I already mentioned, what is the scale factor? So this is the scale factor, standard representation 80, and the density parameter, rho over rho c, and it is defined as density parameter, as you can see, 3h square by a 2 pi z, and the curvature. So these are the standard representation. So total density parameter, which is greater than 1, this leads to closed universe, And if total density parameter means radiation matter plus dark energy, which is equal to 1, that means curvature contribution is equal to 0, and this means our universe is especially flat. But if the total density means the density parameter, sum of the energy density of dark energy, energy density of matter, energy density of radiation, and neutrino is also there, but its contribution is a very less than 1. So this lead to the open geometry. So we have the three types of the spatial geometry: closed universe, flat universe, and open universe. Unfortunately, observation not suggesting closed or open universe, and observation suggests the flat universe. So we have the sum of the three major component of the universe is equal to 1. So continuity equation, this equation not mentioned here, and but you can develop a continuity equation by taking the four divergence of the energy momentum tensor is equal to 0, and solving this continuity equation for constant equation of state, which is the function of a. Why it is a function of a? Because the pressure is a function of a and the energy density is a function of a. A is the scale factor, and of course with the scale factor you can develop it is the function of the redshift also, because in not over a, that is called the redshift 1 plus z. So for the constant, which is comes out like this, and once you fix the equation opposite, w is equal to minus 1 by 3 and uh, 0, then your result will be comes out like this. So I should go little bit fast. So dynamical dark energy, so dark energy either constant, either dynamical. So dynamical dark energy, they have the scalar field model. So in the scalar field model, quintessence is the canonical scalar field. It is a very simplest model. So action, equation of motion, energy density, pressure, Friedman equation, slow roll limit, and power law expansion. These are the mathematical terms, not very difficult. It's a very simple and straightforward calculations. So in this model, phantom case and tachyon ghost condensate. So several scalar field model are here. They all are representing the dark energies that are dynamical in the nature. So two other phantom field and tachyon fields in the same recipe, but the Lagrangian will be different. So switch the Lagrangian in the action and vary the action, the equation of motion will be obtained, and solving this uh, TIK energy momentum tensor of this field, we have the energy density and the pressure. So diagnostic tools also, so there are the different model, different theory. So how one can discriminate this theory? So diagnostic suggested by the Barun Sahani, and that diagnostic is called the OM diagnostics, and it will be constructed by the redshift as well as normalized Hubble parameter. So it is mentioned here, and differentiate this model if the diagnostics value OM diagnostic, which is exactly matter density, present value of the matter density, then cosmological constant, and if OM is greater than matter density, and matter density which is equal to 0.26, then our universe is dark energy is the quintessence. But if it is less than present value of the matter density, then dark energy can be phantom. So dark energy is cosmological constant, quintessence or phantom will be decided by this OM diagnostics. So till now, uh, the research, current status of the research on the dark energy is not sufficient. So few questions now unanswered. So first, the nature. So nature of the dark energy, only we know it is the repulsive gravity, but what other natures? It is the dynamic or the constant is still unknown. And the cosmological constant problem, as I mentioned here, so cosmological constant one of the simplest candidate, but the problem with this, so observed density, which is as you can see 10 to the power minus 47 order, and in the theory, predicted theory, it should be 10 to the power 74. So huge number of the discrepancy, as you can see 10 to the power 121 mismatch. So this is the one of the big problem, and this problem is open till now, and unanswered. And the time evolution, does dark energy strength vary, challenging with the lambda stadium? Lambda stadium is the standard cosmological model. So what is the current status? So current status, DESI means its full name is the Dark Energy Spectroscopic Instrument, and it is a cosmological project, and they are trying to study the millions of the galaxy for the study of the dark energy. So DESI till the March 2025 suggests the dark energy may weaken over the billions of the years, right? And a standard model of the cosmology: 68% the dark energy, 27% the dark matter, 5% baryonic matter, stand the combined state. And ongoing research, they see Euclid and HEDX. So just like that, they see another approaches. And now it's a very crucial. And I'm just working the quantum gravity also. So quantum gravity connection to the dark energy. What is the connection of the quantum gravity with the dark energy? So these three: vacuum energy link, cosmological constant problem, and the theoretical model. So in the theoretical model, quantum gravity approaches, string theory and loop quantum gravity, and of course others also propose extra dimension or modified space time to explain the dark energy small value. That is a completely apart from the lambda CDM. And unification goal, quantum gravity aims to reconcile the dark energy with the consistent quantum theory. But unfortunately, we don't have the any successful theory of the quantum gravity. They try to explain the dark energy at the very small scale, and no quantum gravity model fully explains the dark energy. So the mismatch drive the research into the holographic brain cosmology and some other new area. So speculative connections are conjectural approach. So dark energy might emerge. Dark energy is not a fundamental theory, but we are struggling to develop the fundamental theory of the dark energy. It is just like the ad hoc. So emerge from the quantum gravitational effect. So Planck scale, but experimental test is not suggesting this types of the formalism, this type of the existence. So untestable. And some future, what is the future of the dark energy, and related to the particle and unparticle. So unparticle theory proposed by the Georgi in the 2007 remarkable paper. The paper was published in the physical review letter on particle physics. So in the unparticle physics, so the particle, they don't have the mass, right? So in the particle physics, the scalar field beyond the standard vacuum energy, they can be related. And of course, beyond the standard model, we have to measured in the FCC and the CERN. FCC is a future circular collider proposed by the next generation particle accelerator being studied in the CERN. And on particle physics, scale invariance means on particle as scale invariance of water dark energy, and missing energy at the LSC, cosmic probe and theoretical shift. So these are the two future approach. And still we don't know, apart from the repulsive gravity, and it is the constant or the scalar field. So a lot of the question, a lot of the research now pending to explore completely the about the dark energy, right? So with this, I'm just concluding and finish. So just like the dark energy, power of the thought is invisible, and it drives everything isotropically each and every possible directions. So keep thinking, keep exploring, right? So thinking beyond the horizon, and questioning the unknown. So thank you so much. Yeah, so questions please.
Thank you so much, Dr. S.D. Pathak. Can we take the questions?
Yeah, please.
Thanks for giving me chance to address your question. Now let's start with the first question. Gurpreet is asking here, what is dark energy and how does it differ from dark matter in the universe?
Okay. So, as I mentioned here in the first second slide, so dark energy, after the discovery of the supernova type 1a, universe is accelerated expansion phase. So, why this accelerated expansion? So, all kind of the energy, they don't have the potential to accelerate the universe apart from the expansion. So we need some different types of energy which have the negative pressure, and the negative pressure leads to the repulsive gravity. As you know very well, gravity, they have the positive pressure, and they have the attractive, but the something, some energy, they have the repulsive gravity, and the that energy having the repulsive gravity known as the dark energy, right? And the dark matter is completely different. Dark matter, the matter, they cannot interact with the electromagnetic radiation or electromagnetic interactions. So they can interact with the gravitation. So unfortunately, all of the detected tool, they based on the electromagnetic radiation, either X-ray, infrared, or gamma ray observatory. So everything that is there depends on the electromagnetic radiation. So if the dark matter, they cannot interact with the dark electromagnetic radiation, so of course they will be completely invisible, but the presence will be there, right? So dark matter can only detect with the gravitational influence, gravitational effect. So that is called the dark matter. So don't be confused the term dark and dark energy and the dark matter. It's a dark term. So dark term is not means it is look like the completely dark. It means lack of the understanding, lack of the present scenario, in the presence of the knowledge about that, and research is still pending. Yeah. So I hope
Thank you so
she
much.
understand.
Yes, I hope Gurpreet, you got your answer from our expert. So Gautam, Mr. Gautam is with us. Mr. Gautam, you can ask your question to our expert, Dr. S.G. Pathak. Mr. Gautam, am I audible to you? You can ask your question to our expert.
Yes, ma'am. Good morning, sir, and good morning, ma'am.
Good
Good morning.
morning.
Yeah, please.
Sir, can I ask a question in Hindi? My English is little bit not
Sure,
good.
sure,
Yeah,
sure.
of course you can. No issue.
हाँ सर, जैसे कि मेरा क्वेश्चन था कि अपन बोलते हैं डार्क मैटर, डार्क एनर्जी, बट क्या अभी तक इसका कोई सॉलिड प्रूफ मिला है एक्सपेरिमेंटल से? मतलब कि ये सब तो अभी तक
Uh,
थ्योरी थी, डार्क मैटर से एक्सपेंशन हो रहा है, ये रीजन है, बट क्या अभी तक इसका कोई एविडेंस मिला है?
हाँ, बिल्कुल एविडेंस है। पहले से तो डार्क एनर्जी की बात हम करते हैं। 1998 में सुपरनोवा टाइप 1 हुआ था। और बहुत एज ए सिंपल तरीके से आप इसको समझिए कि जब सुपरनोवा हुआ था तो उस कितने डिस्टेंस पे हुआ था, उसका ल्यूमिनोसिटी डिस्टेंस कितना था। तो जो हमारे पास थ्योरी थी, थ्योरेटिकली हमने उस डिस्टेंस को एस्टिमेट किया। वो डिस्टेंस ऑब्जर्वेशन के साथ जो डिस्टेंस था, दोनों मिसमैच कर रहे थे, मैच नहीं थे। तो उनको कंसिस्टेंट बनाने के लिए आपको डार्क एनर्जी की जरूरत पड़ रही थी। तो इनडायरेक्ट एविडेंसेस डार्क एनर्जी के होने के हमें मिल रहे थे। और भी जो सीएमबी के ऑब्जर्वेशन थे, बाओ के ऑब्जर्वेशन थे, इन सब काफी स्ट्रॉन्ग थे, टाइट थे, जो ये हमें बताते थे कि डार्क एनर्जी शुड बी एग्जिस्ट, डार्क एनर्जी यहाँ पे है। अब बात एक्सपेरिमेंटल टेस्ट का है। सो लैब सिग्नेचर हमें डार्क एनर्जी के नहीं मिल रहे हैं उस स्केल पे, क्योंकि लार्ज स्केल पे डार्क एनर्जी डोमिनेट कर रही है, यूनिवर्स को एसेलेट कर रही है। उस एसेलरेशन को हम अपने सोलर सिस्टम में फील इसलिए नहीं कर पा रहे हैं कि उसका जो डोमिनेशन स्केल है वो मेगा पार्सेक स्केल पे है, कॉस्मोलॉजिकल लेंथ स्केल पे है। तो इसके वजह से उसके इफेक्ट्स हम नहीं देख पा रहे, लोकल ग्रेविटेशन इफेक्ट डोमिनेट कर रहे हैं। लेबोरेटरी में कैस्मियर इफेक्ट एंड लैम्प शिफ्ट कुछ अप्रोचेस ऐसे हैं जो वैक्यूम एनर्जी फ्लक्चुएशंस, वैक्यूम एनर्जी के इफेक्ट्स को शो कर रहे हैं। दैट आल्सो द कैंडिडेट ऑफ द डार्क एनर्जी रिपल्सिव ग्रेविटी की। डार्क मैटर की जहां तक बात है, तो स्ट्रक्चर फॉर्मेशंस, जो गैलेक्सी का रोटेशन कर्व है, वो डायरेक्टली प्रोवाइड कर रहे हैं सिग्नेचर ऑफ द डार्क मैटर। ड्यू टू द प्रेजेंस ऑफ द डार्क मैटर, the rotational curve of the galaxy, that not the Newtonian type, that will be the some plateau that suggests dark matter should be exist. But if these two, dark energy and dark matter, exist, then the problem, what is the fundamental theory, what is the particle structure? So ये अभी तक पता नहीं चला है। सर्न में बियॉन्ड स्टैंडर्ड मॉडल जाकर के भी कोशिश हो रही है कि ये इसका पार्टिकल स्ट्रक्चर क्या है, ये कैसे बना है, इसकी आगे की फिजिक्स क्या है, क्या डार्क सेक्टर में ये 4 फंडामेंटल फोर्स के अलावा 5th फंडामेंटल फोर्स है। तो one my collaborator Maxim Flopo, they provide the WIMS, weakly interactive massive particle. He is the Russian right now in the France. So they just claim the dark matter candidate, they are weakly interacting massive particle। इनका इंटरेक्शन बहुत कम है बाकी बाकी बैरियोनिक पार्टिकल्स के थ्रू, राइट। सो इनके सबके ऑब्जर्वेशन सिग्नेचर है, और दोज ऑल सिग्नेचर आर स्ट्रॉन्ग, दे आर एग्जिस्ट, बट द थियरी इज नॉट कंप्लीटेड। थियरी अभी नहीं है पूरी तरह से सक्सेसफुल। या प्लीज गो नेक्स्ट क्वेश्चन।
yes, Mr.
सर,
Gautam. Yes,
यस,
sure, sure.
या,
सर हमारा एक सेकंड क्वेश्चन था, बट वो इससे रिलेटेड नहीं था।
हाँ यू कैन।
सर, जैसे कि ग्रेविटी अपन बात करते हैं, तो ग्रेविटी के बारे में
हम्म
न्यूटन नहीं बताया और अल्बर्ट आइंस्टाइन नहीं बताया, ठीक है। तो अल्बर्ट
हम्म
आइंस्टीन के हिसाब से जो ग्रेविटी है वो फोर्स नहीं है, बट वो एक इल्यूजन है, स्पेस टाइम कर्वेचर की वजह से आता है।
हम्म
बट न्यूटन न्यूटन जैसे बोलते हैं कि नहीं, दो हमेशा ऑब्जेक्ट हमेशा अट्रैक्टेड फोर्स करते हैं, मतलब कोई भी दो चीजें हमेशा वो ऑलवेज अट्रैक्ट करते हैं एक दूसरे को।
हम्म
तो अब
हम्म
मेरा जैसे कि क्वेश्चन था कि जैसे आइंस्टाइन ने बोला कि ग्रेविटी अपन को फील होती है क्योंकि स्पेस टाइम में कर्व होता है, उसकी वजह से अपन को फील होती है, इल्यूजन होता है। तो
हम्म
जैसे कि अपन दो बहुत बड़ी बॉडी जिनका मास सेम हो और अपन उन दोनों को एक दूसरे से मतलब कि थोड़े डिस्टेंस पे रखें स्पेस में,
हम्म
तो
हम्म
क्या उन दोनों के बीच में कोई फोर्स होगा? क्योंकि अगर न्यूटन की बात माने तो फोर्स होना चाहिए, G m1 m2/r²। बट अगर न्यूटन की माने तो फोर्स नहीं मतलब आइंस्टीन की माने तो फोर्स नहीं होना चाहिए, क्योंकि दोनों ने सेम कर मतलब कि स्पेस को सेम मोड़ा होगा, क्योंकि उन दोनों का मास सेम है। तो अगर न्यूटन मतलब आइंस्टीन बोल रहे हैं कि फोर्स नहीं होगा उनकी थ्योरी के हिसाब से और न्यूटन की थ्योरी के हिसाब से होगा, तो मतलब कौन सही है कौन
हम्म।
गलत है?
देखिए गौतम जी, क्या सही है क्या गलत है, डिसीजन इज अ वेरी वेरी डिफिकल्ट. सो फर्स्ट ऑफ ऑल, देयर आर द so many things mixed together. The theory of the gravity, according to Newton, is something different, and according to Einstein, it's the different. So these two theory completely different, and we cannot mix these two theory club together. Newtonian approach was the initial approach, and he just give the how much the strength of the gravitational force, but they unsuccess to explain what is the origin, how the gravity originate, how this force will comes out. They just only tell the strength of the force, but they unable to explain the how the gravity will comes out. Einstein asked the question, and just give the gravity is not a force, it is a manifestation of the space-time structure. They are the very bold idea, and completely against to the Newtonian gravity. So yeah, you are right. Gravity, according to Einstein theory, it is the manifestation of the space-time structure. So mass tell us space-time will be curved, and the curvature tell us how the particle will be moved. I repeat the same things. मास डिसाइड करता है स्पेस टाइम में कर्वेचर है, और कर्वेचर डिसाइड करता है कि पार्टिकल कैसे मूव करेगा. This is the fundamental approach of the general theory of relativity. So, but if you switch the some other theory of the gravity, so where the gravity is the something different, right? So one things I would like to clear here, till now we don't have any successful theory of the gravity. There are the huge number of the theory of the gravity proposed by the different researcher, emergent gravity or modified gravity, and quantum theory of the gravity also. So none of the any successful of the gravity. So whatever the questions you are taking, it is depends on the model, in which model you are working, right? So for example, one is the thought experiment. Somehow if the sun is eliminated, so after the how much time you will receive this signal, you will feel it, there is a no sun and earth is moving in the circular orbit. So of course the answer will be depend on the model, right? If you believe in the special theory of relativity, so after around 8 minutes you will know that there is a no sun and earth follow the circular path. But if you believe in the Newtonian gravity, so gravitational signal, gravitational force can propagate with the speed, infinite speed, so quickly you will know it. So what is the right and wrong, and this will be decided by which model you are working. आप किस मॉडल पे काम कर रहे हैं, कौन सी थियरी आपने अडॉप्ट किया है, उस थियरी में उसका एक कन्विंसिंग आंसर बनाया जा सकता है. ठीक है. तो ये दो थियरी को हम मिक्स नहीं कर सकते, क्वांटम थियरी क्लासिकल थियरी को मिक्स नहीं कर सकते. जिस थियरी में आप हैं आपको उसके हिसाब से आंसर मिलेगा. सो इफ यू चेंज द मॉडल, आंसर विल बी द चेंज. आई होप
ओके।
क्लियर टू यू.
हाँ। सर क्या आप हमारे लिए कुछ बुक्स बता सकते हो ग्रेविटी के ऊपर, जो मतलब सिंपल बेसिक जिसपे थ्योरी ज़्यादा हो और मैथमेटिक्स कम हो, ग्रेविटी को और अच्छे से समझने के लिए?
हाँ बिल्कुल. इस पे नालिकर की बुक है, जन नार्लिकर की यूनिवर्सिटी प्रेस से एक पतली सी बुक कॉस्मोलॉजी की आती है, जिसमें इजी मैथमेटिक्स दिए हुए हैं, कोई टेंसर और कुछ इस तरह के प्री रिक्विजिट्स की जरूरत नहीं है, आप उसको पढ़ सकते हैं. कार्ल सगन के भी बुक है कॉस्मोस. सो इंटरेस्ट के
अच्छा।
लिए अच्छी बुक है. और आप हमारी
कार्ल।
यूनिवर्सिटी में भी आ सकते हैं. हमारी यूनिवर्सिटी में एस्ट्रोफिजिक्स से एक स्पेशल कोर्स बीएससी और एमएससी में चलाया जाता है. तो ये मैं इसके क्लास लेता हूँ. सो द स्टूडेंट्स दे आर ज्वाइन दिस लवली प्रोफेसर यूनिवर्सिटी, especially the astrophysics course. So this is the one university in this side, they are running the course in the astrophysics properly in the BSc and MSc.
ओके।
Yes,
Mhm.
I hope, Gautam, you got your All answers are from our expert, Dr. S.D. Pathak.
Yes, ma'am. Thank you, sir.
Thank you.
Thank you.
Thank you so much. And you have, if you have any questions regarding admissions, you just write on us at admissions@lpu.co.in. If you you can do WhatsApp chat with us. Our WhatsApp number is 98525 69000. I'm repeating the number. It's 98525 69000. Once again, thanks to our expert, Dr. S.D. Pathak. Uh,
Welcome.
as we come to the end of this webinar, I want to express my deepest gratitude to our experts for sharing their valuable insights and expertise with us. Your presence, enthusiasm, and active participation have made this experience truly special. Hopefully, the attendees found this webinar to be valuable and will be able to utilize the information for better decision making regarding admissions. If anyone wants to access this webinar again, they can visit our website, that is lpu.in, or can be accessed on YouTube also. Stay connected with us for future webinars. Until we meet again, with the permission of my seniors, I would be signing off this webinar. Take care and goodbye. Have a beautiful day.
Thank you.